All right, this is the video on Newton's second law. So just to review some concepts that we need to know about inertia. It is the property of all material bodies to resist a change in their motion. We define mass as a measure of the amount of inertia a body possesses. So Newton's first law of motion is known as the law of inertia. Objects at rest remain at rest, and objects in motion remain in motion in a straight line unless acted upon by an unbalanced force. Now, basically what this is saying is that net forces cause acceleration. So if there's a net force applied to an object, that body will accelerate. If it accelerates, there must be a net force applied to it. So essentially, net forces apply acceleration. Acceleration implies net force, so that a net force must have been applied, right? So if you look at this little equation down here, net forces imply acceleration, and acceleration implies net force. That is Newton's first law of motion. Now, what is the relationship between acceleration, net force, and mass? So that brings us to Newton's second law of motion. It is known as the real law of motion. And it's this big, long paragraph, but essentially it's just written as the equation, right? So it's essentially saying acceleration equals the ratio of net force to mass, right? It is the ratio of net force to mass. So acceleration equals net force divided by mass. So when Newton's second law of motion, Newton quantifies how much acceleration is produced with any given net force. And here's the ratio part, right? The amount of acceleration produced depends upon the ratio of net force to mass. So when we're talking about Newton's second law, I always say you're going to get tired of hearing the word ratio, right? Because acceleration is the ratio of net force to mass. So let's just take a look at a shopping cart. We'll look at the shopping cart while it is empty. Then when it is full, it is on wheels, so we can ignore friction. The person will be applying the same force in both scenarios. So we're going to compare the empty shopping cart and the full shopping cart. So which cart, if any, resists a change in motion more? It's going to be that full shopping cart. And just think about it this way, right? If you're pushing these shopping carts and you're trying to turn down an aisle, which one is are you going to feel that resistance to change in motion more? It's going to be the full one. Which cart, if any, has more inertia? It's going to be the full shopping cart. And which cart, if any, has more mass? It's going to be the full shopping cart. I love these three questions because they are the same question. We use mass to measure inertia. Inertia is resistance to change in motion. Now, which cart, if any, has a larger net force being applied to it? Well, if we're ignoring friction, then the net force is going to be the applied force. And we said that this person is applying the same force in both scenarios. Now, the gravity, that weight, is going to be balanced out by the normal force in both these scenarios. So it's going to be the same net force. So which cart has a larger acceleration? Well, think about it this way. If I'm pushing both these carts with the same force, which one is going to accelerate more? It's going to be that empty one. And which cart, if any, has a larger ratio of net force to mass? It is going to be that empty one, because acceleration is the ratio of net force to mass. So here's what I'm talking about. Well, I've got a small mass and I'm applying a net force to it. If I look at the ratio, I've got a pretty large ratio because it's such a small mass, and the acceleration is going to be the ratio of net force to mass. Now let's just say I have a large shopping cart, large mass, but I'm pushing with the same force. Notice how, because that mass is larger, the ratio is lower, which means the acceleration of that cart is lower. So in order to determine, let's just take a look at how they're affected. We did this fan cart simulation. So in this one, we place all the fans on the cart, and you click the bar chart tab so we can see those numerical values. Now, this is where the acceleration of the cart will be found. So what you're doing is, on this one, there's fans on the cart, and there's no boxes on it. What you're doing is you are turning each of these fans on, right? So you keep the fans on. You'll notice that each of those fans applies a larger net force. The mass remains the same because we're keeping the cart on the same, and you can calculate the acceleration, right? It's net force divided by mass, but it gives you that. And then what you can do is you can graph it. Net force acting on that cart, well, it's going to be a linear curve that way. Now this one, what we did was we had all three fans on, and now we're putting boxes on there. So now we're increasing the mass. So now I've got same force but larger mass, and I can calculate the acceleration. And now what you do is, we just wanted to draw the free body diagram. withdrawn. How could it be? So we draw the free body diagram of the cart. This is what it's going to be. Now, the question is, looking at the free body diagram that was drawn, how could it be determined if the cart is accelerating? There's an unbalanced force acting on it, right? An object will accelerate if there is an unbalanced force acting on it. So now these last few questions, look at the acceleration versus net force graph. If the mass of an object remains the same, what is the relationship between the acceleration of that cart or that object and the net force applied to that object? So you come down here to these like these graphics, and you can see that it's a linear curve, right? The rise over run, it's a linear curve. So it's the acceleration is a linear dependency on that net force. Now, look at the acceleration versus mass graph. If the net force applied to that object remains the same, what is the relationship between the acceleration of that object and the mass of that object? Well, you can see here it's going to be this inverse graph, right? So it's going to be inversely relationship with mass. So the larger the mass, the smaller the acceleration, and it's going to be a y equals 1 over x relationship. So now we can actually put this relationship to the test with this CART lab. So in this lab, we're using gravity as the counterweights to be used to apply a force to the cart. Manipulate or erase the arrows to the right, draw the free body diagram for the forces acting on the counterweight. So we're going to have these counterweights going up, and it's going to be pulling on that string. So I do have a tension force, but I've also got a large gravitational force pulling on it as well. And you can see here the weight, that force is going to be either half a Newton and 1 Newton. So we're increasing that force being applied to it. So we use the spring scale to determine, hey, what's that force pulling down on these counterweights that we're going to use to apply to that cart on the table. So now we're going to use the gravity. Those counterweights are going to be used to apply a force to the cart on the table, manipulate and or erase the arrows to the right to draw the free body diagram for all the forces acting on the cart on the table as the counterweights are falling. So we're assuming the wheels are no friction. So I can see here I've got a tension force, that rope is pulling on it. Gravity and the normal force are going to be balanced out. So I do have an unbalanced force. It will be accelerating. So if we look at this here, the cart pulls on the metal cylinder, and the cart will have a combined mass of 0.6 kilograms. And we did time how long it takes to get from the counterweight release to the time the counterweight hits the ground, just so we can see that there's a difference, that there is a larger acceleration here. So notice what I did was I used Newton's second law. I know that when I drop that counterweight with 50 grams, it's going to pull with half a Newton, and I know that the combined mass of the cart, I can calculate the acceleration, net force divided by mass. Then I put another 50-gram mass on it, and now I'm applying 1 Newton of force to this same mass, and notice, well, it's accelerating faster. It got there in a shorter amount of time because of the ratio of net force to mass. So let's look at these conclusion questions. What is resisting the net force of the counterweight pulling on the cart? The cart's inertia or weight. So it's going to be the cart's inertia. And explain your answer. Well, gravity is pulling down, right? We're not pulling against the weight of the cart. Gravity is pulling down. We are pulling horizontally. So at no point is that gravitational force pulling down resisting that pulling motion. It's going to be the inertia. What happened to the acceleration of the cart when the mass of the cart remained unchanged, but the net force being applied to the cart by the counterweight increased? So what happened was, I say use the word ratio in your answer. So now we increase the net force being applied to that cart. So what's going to happen is that I increase the ratio of net force to mass because the mass remained the same. So what's going to happen is the acceleration is going to increase. Now, using Newton's second law, what would happen to the acceleration of the cart if the net force being applied to the cart remained unchanged, but another half kilogram metal cylinder was added to the cart, increasing the cart's mass? Explain your answer. Use the word ratio in your answer. So now let's take a look at Newton's second law. So now I keep the same net force being applied to the cart, but I put another like mass on top of that cart. So now I've got a larger mass. So if you look here, the mass, that bottom value is going to increase, which will decrease the ratio of net force to mass. Thus, the acceleration will decrease. Now, if you perform this experiment on the moon where the gravity is 1/6 that of Earth, how would the results of this lab change? How would the results of this lab remain the same? Hint, what is providing the net force? How could you change the setup of the lab to ensure the results of this lab would remain unchanged on the moon? So in this one, yeah, it would change your results because we are using gravity for the net force. We're using that force of the counterweight to pull on the cart. So that would change. But it's not because that inertia of that cart changed. So what you could do to ensure that this lab remains unchanged on the moon or the International Space Station once we remove weight from the equation is whatever's applying that net force can't be dependent on gravity. So it could maybe be a spring, or you could just have a spring scale and pull on it. Say, hey, pull for 1 Newton, right? And you could watch it accelerate. That would ensure that if you did this experiment on the moon, if you did this experiment on the International Space Station, it would remain the same. So why can't a ping pong ball be thrown very far even though it doesn't have a lot of mass? So the thing is, if you're throwing a ping pong ball, it doesn't have a lot of mass. You can accelerate it very quickly, but the instant it hits the air, what's going to happen is because it has such a low inertia, that air is going to have a larger effect on the acceleration, will slow it down. So if you removed all of the gravity, or not, if you were not gravity, sorry, if you removed all the air, a ping pong ball would go really, really far because it's you could get it accelerated real fast because it resists that change in motion really less, and there would be no air resistance to slow it down. So that's the reason why, right? If I have a ping pong ball and I throw it, I could throw a golf ball or a baseball a lot farther. Even though that ping pong ball has a lower mass, it's because it's affected by that air resistance more. So let's take a look at the spilled water lab. So what you're doing in this lab is there is a cup with a hole in it, and you are going to fill it with water. So with the cup filled with water completely and your finger covering the hole, put the cup over the bucket and pull your finger away from the hole while still holding the cup. So what happens? Well, that water should fall out the bottom of the cup. Now with the cup filled with the water halfway and your finger covering the hole, put the cup over the bucket and drop the cup, record your observation. So what's going to happen is as you drop it, if you drop everything, even though there's a hole in the bottom of the cup, that water is not going to come out the bottom. It's not going to come out that hole. It's not going to go out the top of the cup. It's all going to fall at the same rate. And then you do this again, but you fill it all the way, and you're going to get the same results. The water doesn't go out of the cup upwards. It doesn't go out the hole on the bottom of the cup. It all falls at the same acceleration. So I had you draw the free body diagrams for all these different scenarios, right? One where you're holding like the water in the cup while you're holding it. I had you do one where the water in the cup as you let go, right? So notice the cup still has that normal force being applied to it, but the water does not. That's why it falls out the bottom. And notice that, okay, well, as the water is in free fall and the cup is in free fall, they only have gravity being applied to it. So in order to answer the conclusion questions, let's just talk about one of these. Why do objects fall at the same rate in a vacuum? So let's just take a look at Newton's second law here. So if I've got a tennis ball and a medicine ball, which ball do you think will hit the ground first and why? Well, they're going to hit the ground at the same time. Now, if I look at this as the balls are falling, are they traveling at a constant speed or are they accelerating? Well, they're going to accelerate because there's a constant force being applied to it, a net force being applied to it. Now, which ball do you think has a larger gravitational force being applied to it? Well, this is the misconception most people make is they think because, well, they hit the ground at the same time, gravity must be pulling with the same force. That's not true. Remember, the gravitational force is the weight. If you hold a tennis ball and a medicine ball out, you can feel that gravity pulling harder on the medicine ball. It weighs more. Gravity's pulling on that medicine ball a lot more. But which ball resists that force more? It's going to be the medicine ball, right? And that resistance is called inertia. It's resisting that force more. All objects fall at the same rate because gravity is pulling on larger objects with a larger force, but they also resist that force more. All objects falling have the same ratio of net force to mass. So if we take a look at this example, well, yeah, the tennis ball has a very small mass, very small resistance to change in motion. You can toss it around in your hand, real easy to change its motion, to accelerate it. But it also has a small gravitational force, if we're ignoring air resistance, right? So it's got a small gravitational force. Now, if I'm looking at this ratio of net force to mass, yeah, it's going to give me the acceleration. Now, I've got a larger medicine ball. It has a very large mass. If you're tossing it back and forth, you can feel that resistance to change in motion. Large mass, large resistance to change in motion, but it also has a very large force pulling it down. So if I look at the ratio of net force to mass, it's going to be the same ratio as that tennis ball, right? So those larger objects, yes, they have a larger gravitational force pulling them down, but they're resisting that force more as well. And it just so happens the ratio of all objects falling is going to be the same. It's going to be the same. So if we look at that, right, use Newton's second law to explain what happens when the cup has water in it and it is in free fall. Use the word ratio in your answer. The reason why the water doesn't fall out the bottom of the cup as it's in free fall, even though that water has more mass than the cup, is because the ratio of net force to mass is the same for the cup and the water, right? That water has a larger gravitational force pulling on it, but it also resists that force more. Now, all objects on Earth will fall with the same acceleration. Explain why don't heavier objects fall faster than lighter ones. Use the words gravity, inertia, and ratio in your answer. So I just gave you a little help there on that one. So essentially what happens is that those larger objects, yeah, gravity's pulling on them a lot more, but they also have a larger inertia. They resist that force more. So the ratio of net force to mass for all the objects is going to be the same because larger objects, yes, larger force pulling down, but they resist that force more. Now, if we look at this last one, if you were to perform this experiment on the moon, where the gravity is 1/6 that of Earth's, how would the results of this lab change? How would the results of this lab remain the same? Well, it would change because, well, it would fall at a slower rate, right? But we would still see the same thing. The water would not come out the bottom of the cup. It wouldn't come out the top of the cup. And the reason why is because, well, even though we're on the moon, yeah, the ratio of net force to mass is going to be the same for the water and the cup, but it's going to be a lower ratio than on Earth, right? I think it's like 1.6 something. So you would see it accelerate at a lower rate, but you would still see the same result. That water would not come out of the cup. They would fall at the same rate. So once again, there is just too much unknown in the universe to take a break from learning. Get out there and question everything.